Okay, thank you for the invitation, Nikos. Thank you for listening here at this presentation. My name is Paolo Mercorelli, but I will tell you about me and about my research a little bit later or after the presentation. Let me start, nevertheless, with a small videos in this sense, which we can see here, the device which I would like to present today. And the name is ice clamping, in the sense it's a device which is used for fixing workpieces before milling or before machining, and it's basically the idea is to fix an object using the frozen water. Yeah? The idea is to control the temperature. Yeah? We will see now in a few seconds. In order to fix, we can see here using the ice, the piece on the platform to be, let me say, milling, or in any case, to work on this piece here. Once the temperature is ready, I mean, when the ice is ready to fix the object, we can work on. We can see here as because of this tool, the temperature change on the object. This means the idea is to control. The temperature such that the object remain fixed during this machinery, in this sense. And this sense is problem control. It's easy to understand. Why this motivation? We will come back on the motivation. The motivation is sometimes we need really a system which fix the object without deforming it. For instance, for delicate system, for fragile systems. Yeah, but in general, it seems to be more economical to use this kind of method instead of a grasp, excuse me. Instead of a robot, in this sense. First of all, we don't want to deform the object. We can see here a little bit we can see here the temperature, how it changes somehow the humidity of the element of the object, if you want. This means change somehow the mass. Go ahead. We can see how it fixes this without using any grasp. The project is together with a company in Germany. And we can see also for unclamping is extremely easy, because to remove the object is enough to reverse the polarity of the current. We can see how quick we can, just a few seconds to remove the object. Okay, let me now switch on the presentation, and let me tell you about this mathematical insights. And we can see here the title, Mathematical Insight for Advanced Ice Clamping Control in the concept of Industry 4.0. We will see why Industry 4.0, but in any case, this advanced, let me say, method to fix is already something which can be considered inside a new, let me say, horizon for such kind of application, but not only. The talk is organized in, let me say, 5 parts. Now, we will see an introduction, which I try again to emphasize the motivations, and we will see how is important the system model in the second part, because it's a control problem. In order to obtain robustness of the control systems, in order to be insensible with respect to the uncertainties which we have in the system, in order to be insensible with respect to the disturbances which we have inside an environment, it could be very noisy because of the Industry 4.0. Nowadays we try to digitalize everything. This means interferences between systems must be taken into consideration. To handle these problems, we tried, at least today, I tried to introduce 2 methods. One is how we realize the virtual sensor, because we will see that it's not very easy, or it's not suitable to measure the cold temperature, because we have the piece. This means the idea is to measure the hot temperature, but to estimate the cold one to be controlled. Why Kalman filter? We will discuss shortly this. And also we need a robust, in the meantime, a robust control system for the reason which I told you before, because of interferences, because we don't know exactly the parameter of the models, because the parameters change over time. We have seen also the humidity change the mass of the object to be milled. Yeah, and then I show you some results. The project started some years ago, and in cooperation with the company, the company which is basically is in Lüneburg, I would like to say. Just a few words about the system. I sketched here the system which we already seen in the movie. We can see here in the lower part, the sink is basically used for cooling, because we can see that we have the Peltier elements in the plate. Let me say, the plate consists of an upper part and the lower part, because if you remember a little bit this Peltier, I will come back on this Peltier effect. Let me say, with current or voltage, we can realize basically two different temperature with respect to the opposite plates. In the upper part, for instance, we have the cold temperature. We can froze the system. We can realize ice to fix. We can see here a little bit upper part, and the lower part for the, I would like to say, conservation principle of energy. We realize in the hot part and hot temperature in this part. We can see here the workpiece, which basically in the sketch, which we have seen in the movie, and then the tool. Again, the real system, which is decoupled here exactly the platform which we have, but here we have nevertheless here is basically this heat sink, and here our Peltier elements, and here we can see the tool. Just to realize a little bit more concretely what we are doing. But anyway, the movie was, I think, relatively clear. We have different also configurations and different structure. We can see here, for instance, in a product which we realize with this company, which we have in a matrix. Let me say a matrix with 12 let me say thermoelectric cooling system with 12 unit elements, if you want. We can see here a little bit, I will tell you later, that extremely important is the map of the sensors. But please pay attention, the sensors are in the lower part, basically in the hot part, because of course in the upper part, when we are cooling, we have basically the system, probably you can see here, or the object or the workpiece, which is clearly, it is much better to have a plate which is free from sensor for different reasons, also for logistic aspect, but also because sometimes vibrations on can broken down the sensor. Yeah, thank you. Yeah, about that I already told you. Basically, the motivation is that we want to obtain. We want to fix an object without deformation. This is the main motivation. Not only, of course, grasps or robots to fix. This is more, let me say, costs more, is more expensive than water and the sense. Of course, it's not only water, because we have to organize control systems. Anyway, we have something more. But anyway, the robot could be more expensive, but not only the risk that we have something which is broken down. Yes, it seems to be less. If you read some literature, sometimes you have a different, let me say, nomenclature. We speak about adhesion, cohesion, but it's not the topic of today, because this is more related to the physical aspects. Let me go through the introduction. Just a few words about some references. Considering our aspirations and our background, we can see that the keywords here could be considered, manufacturing, if you want. We can see the first two papers which inspired us for this project, but also we can see our publications. which we can see the last two publications, basically last year. And when we conclude the first part of the project, we can see in the publication on IEEE transaction on industrial applications, in which we can see that nevertheless the community, the reaction of the community was quite positive in this, on this topic here. Okay, let me summarize basically the aim of the lecture. We will see together why in the context of Industry 4.0 is important to speak about the robustness of the control systems. The control systems, because we tested more than one. Today we will see one possible configuration. Again, the main motivation is zero deformation, we can see here in the middle of the text. And of course, the robustness of the control systems is quite important, because we don't know exactly everything on the system. We have to say that the parameters change over time. We have seen also, I told you about the humidity, which is removed during the milling phase, change also the mass of the object. Also interferences between elements in between or in the environment can generate problems. Therefore, we are proposing not only in this configuration, but in other possible control configurations, robust method. Today, I will tell you about the uncentered Kalman filter shortly, because it's a relatively complex mathematical method, model-based, and the backstepping, let me say, control system, together with a feedback, let me say, input-output, to be precise, linearization. The choice of these two methods are basically related to the robustness of that. About that, I already told you that we have a mass, which is we don't know. I would like to add just that the model is based on the first law of the thermodynamics. Let me give you another picture, and then we will start with the mathematical model. We can see here a little bit more concretely. But I don't know. But anyway, we can see basically two conductors which we can feed this device, the Peltier cell, which is the basic cell of our system. We can recognize a little bit the cold side, the hot side, which I already explained a little bit. Of course, we can consider very large or very large plates. We can put close together many elementary, let me say, cells to realize our desired surface in accordance with our necessity. Now let me go a little bit more inside on the mathematical aspects. In particular, for us, I imported the equation 2 and the equation 3, which came from the equation 1, which is the power balance, which can be sketched we can be seen here in this picture, in which we can see that we have an input which can be considered the current. In fact, basically we control the system using let me say the current, using transistors, and we can see that with the input of the current we have the power transmission, let me say, in a power transaction between the cold, let me say, plate through the hot one. In general, the equations which we use for this is new in the literature, which I cited, the equation which we need for observing, to realize the Kalman filter and to control the system are the dynamical, let me say, the dynamical equations we can see here because of the presence of the derivative, the nonlinear differential equation. This means, we use the equation 2 and equation 3, which state, these two equations state the dynamic of the temperature, TH, hot temperature, and TC, cold temperature. They are the state, the physical state in accordance of our model of our system. The input is the current. We can see the nonlinearity in the input, current square, but also we have a nonlinearity between the input and the state. We can see here the multiplication between Tc and I, Th and I, and this basically is the well-known Seebeck effect. In the sense, the parameter S is important to be known, to control, but not only to observe. Very often in the literature we find an approximation of the parameter S, which is not exactly a parameter, it's a function of the temperature, using polynomial, let me say model, polynomials in a function of the temperature. Let me go ahead, because in our system we will see that it's not extremely important to know exactly this function S, let me say parameter, Seebeck coefficient. The literature is known as Seebeck coefficient, but of course this coefficient changes over time because change the temperature. Also, as I remarked at the beginning, the mass MA, the mass of the cooling plate, which basically is together with the mass of the piece which we want to fix, change because change the amount of water, the humidity. It's not exactly important to know perfectly everything, because we will see that, I will tell you at least, but probably know that using the Kalman filter and using this method of control, or this method to control, we have, let me say, something which is not so sensible with respect to the change of these elements, or let me say, is sensible, but nevertheless we can achieve our goal. About that I already told you during this introduction, let me say, power balance which generate, which can represent physically our system. Let me go through the system modeling, just introducing the scheme, the control scheme, which, as I already told you, is model-based. But we can see here that our system to be controlled with a disturbance, which basically is the power disturbance. We can see here I didn't put it probably in the future, in the next slides. Basically, is the introduction of the disturbance. This means when we are milling, of course, I change the temperature of my object. This means I can consider let me say an input as a disturbance, of course, which changes the temperature. This is an external power which we change the temperature which we want to control. Tc is the variable which I would like to control. The control system is basically organized or consists of two parts: an observer, which is able to basically to estimate the cold temperature, and not all. We can see here I estimate also the hot temperature. I will estimate the disturbance, exactly this one, and sometimes it's useful to control also the variation of the disturbance. dP is the variation of the disturbance. Measuring what? The current in input. I told you that our input is the current, and as I told you at the beginning, the hot temperature, basically the temperature on the lower part of the plate, in order to have the upper part of the plate free of sensors. Yeah, the motivation I already told you is the robustness. No? Is basically the robustness. Sometimes I don't know parameters. Sometimes I have disturbances which is connected with the interferences, and this is basically the motivation. Let me now start introducing the mathematical model for the controller. The mathematical model for the controller is a mathematical model which consists of an augmentation of the model, because, as I told you, we have just two models, at least in our representation, two equations, better to say, two equations which represent the physical system. Now we can see that we are introducing an artificial, let me say, an artificial mathematical model. Why that? Because I would like to emphasize that the model which I presented before is not an affine model. I don't know if you are happy to work with a nonlinear system. Let me go ahead so we can understand better here. Yeah. An affine model is a model which can separate the input with the state. If you remember, probably it is good to come back on our physical, let me say, model of our representation of the physical system. We can see here that basically the input I is mixed, let me say, or let me say also I mix the states. This kind of mathematical representation has some drawbacks, at least to realize the control. Introducing or augmenting, let me say, the states, basically when considering now the current as a state, and I will consider an artificial input UI inside the microcontroller. This means inside the possible representation, we can see that I can maintain nevertheless the two physical, let me say, differential equation will represent our system, and in the microcontroller I try, let me say, to approximate the current using an artificial, or let me say virtual current UI. Again, this is basically the equation which we implement, moreover, in the sense of augmentation in the microcontroller. We have the advantage now that the representation inside the microcontroller of the model is affine. We can see that we can distinguish the input with the states. The input is UI, it's an artificial input, a virtual input. But of course, we have some drawbacks. The most important, let me say, drawback is the zero dynamics, or let me say the internal dynamics, because augmented states, of course, we have something which does not reflect the physical system, and this something is inside the representation of this new, let me say, augmented model. Of course, we have to guarantee that this internal dynamics, what happens inside the microcontroller, is at least stable. This representation here, or this state representation, we will use for the Kalman filter. Why that? Because we augment also here the state, considering the disturbance and its derivative, because let me come back, excuse me if I go up and down, because for our controller we need, or at least it's suitable, or it's easy for the controller if I have more information about what happens on the system. Okay, let me tell you a few words about the possible discretization of this model. Here, in the context of a Kalman filter, we tried with forward Euler. We have some kind of problems because our sample time is quite large. Inside this sample time should be implemented the observer and the controller. This means, if I don't know if you have it with some kind of problems, if the sample time is quite large, we cannot, at least using feed-forward Euler, we can have some oscillations in the representation of the variables, and then this is reflected in the controller. At the end, we try different methods, but we converge on the Runge-Kutta method, which it seems to be more suitable for large sample time. Of course, Runge-Kutta method is the method with some drawbacks. It's an implicit method. The mathematicians understand very well this implicit method. This means we have to use some tricks in order to be able to use. Implicit means that very often it is not clear what is the cause, what is the effect. Mathematically, the left part is also in a function of the right part, is mixed, and this means we have to use some approximation. But with Runge-Kutta we obtain better results because it's more able to work with larger sample time. About the Kalman filter, I would like to sketch a little bit the idea, because in particular the ascended Kalman filter is a method quite, let me say, complex, but when we use ascended Kalman filter instead of extended Kalman filter, if the nonlinearity which we have in the system is quite strong, even though if I say quite strong, it's not clear what I intend, because it is difficult to measure when is nonlinearity strong is not strong. But in the context of Kalman filter can be a little bit evaluated in the sense the extended Kalman filter is nonlinearization in the corrected point of my nonlinearity. And then let me say, if this Taylor linearization generates and relative big error which we can evaluate also in the estimation, sometimes it's useful to think that not increase the element in Taylor, but increase the number of points in which I linearize. This is the basic idea of the ascended Kalman field, and then at the end we try to summarize, we can see here, the different linearization in different points without increasing the level of the Taylor approximation. This means the number of the derivative which I implemented. Very important is the choice. Is the choice of this point in which I linearize my system. The name is a sigma point. This is a critical point. We have some heuristical method to localize or to choose the sigma point. Yeah, I don't want to go more in depth here, but I will try to summarize, and the equation is very heavy, we can talk a little bit later. I can to summarize everything with this scheme. I don't know if it can help. Eventually I can come back to the equations now. Basically the idea is to realize or to map my nonlinear system with different working points. The working points are basically calculated by the approximated, or better to say, the corrected elements on the previous steps. And using this map, we approximate the nonlinearity. We weight the approximation. We can see here at the beginning, as I told you before, we weights. Also, how we choose the weights is a little bit heuristical. To have just at the end one possible estimation of my state vector. Again, here the state vector is represented by hot temperature, cold, better to say cold temperature, hot temperature, disturbance, and the variation of the disturbance. The rest of the Kalman filter ascent in this case is quite similar. It's quite similar to the extended, but in any case, we can see that we have different elements. For instance, here, I don't know if you have it to work with the Kalman filter. The equation 22 and 24 are exactly the same, almost exactly the same in an extended Kalman filter, in which we can see that the a priori estimation, which is also calculated with this sigma point. Sigma point means different points in which we approximate the nonlinearity, is corrected using the innovation, what I am measuring minus what I am, let me say, observing, also weighted in this sense, multiply the k. K is Kalman gain that in the ascent is calculated a little bit different because again, we have a different or more than one point which we approximate the nonlinearity. Let me conclude. I would like to tell you concluding about the controller. The controller needs, as I told you, cold temperature, hot temperature, and possibly also disturbance, the variation of the disturbance. As I told you before, we have three equations. One equation is the augmented equation, and once we certify that the zero dynamics, the dynamics that don't affect the output, this means the scalar product between the derivative, the variation of the zero dynamic multiplied the map of the input is zero, don't come out, but nevertheless it's important for us to certify that the zero dynamic is at least stable. The reason is, we can see the reason is that the microcontroller should be not generate overflow in this sense. Once we certify this one, we can find in a very easy way, as let me say, in a relation between the input and the desired output, which basically cancel everything and realizes my goal, which is my desired cold temperature problem. When I say cancel everything, cancellation is a mathematical concept. An engineer, when we say cancellation, we cannot cancel because we don't know the parameters. Idea to robustify the control system and to use these backstepping techniques. Backstepping means we have in this case two steps. to realize the controller, which is Lyapunov place. Lyapunov is probably somebody knows about the Lyapunov method, which is structurally robust, because we will see at the end is based on an inequality. If the inequality is somehow guarantees, we guarantee the stability, the convergence. Of course, if I know better the system, the convergence could be better predicted. Otherwise, we cannot predict exactly, but nevertheless it guarantees. Again, to sum up, the Kalman filter realizes statistically estimation, robust estimation, because it's statistically based of the states, and then the states can be used to control. Just a few words about the controller. The first step, we are considering just the error between what we want to obtain, a desired temperature, minus what we have. We measure the cold. You remember, we estimate the cold. We estimate the cold measuring the hot temperature. We can see after some relative easy calculations, we can realize that the first Lyapunov function, the first step, is negative. This is the theorem of Lyapunov that guarantees the stability. This means stability in the sense of a convergence of Tc toward Tc desired, if we have a positive function, and if its derivative is negative. We need an artificial, let me say, input, alpha, which basically should be, if you think, equals Tc derivative. If you look at this equation here, if alpha equals this one here, I cancel Tc derivative, I will obtain this equation here. But how I can realize alpha? Yeah, alpha is realized using basically the second step, which should guarantee that alpha equal Tc derivative, as I told you here, in order to cancel alpha is so conceived, A1 is the error between what we want to obtain, what I obtain. And in any case, after some easy calculation, I can obtain E2 derivative. As I told you, E2 is the derivative of E1. Very important to conclude and to have a constructive aspect, or a constructive, let me say, input equation. I have to consider just one Lyapunov function, which include everything. Lyapunov is basically an energetical method. It means we need one Lyapunov function to describe everything in order to be sure that we include all possible states or possible dynamics in the energetical balance in this sense. Also, the calculations is relatively easy, a little bit boring. I do the derivative of V2. V2 is positive, as I told you, in accordance with the Lyapunov theorem. I have to demonstrate that V2 derivative are negative. Yeah, after some easy calculation, the key points, I am concluding now, that C3 and C4 is enough to choose C3 and C4 positive. Of course, this is a little bit arbitrary. The speed of a conversion depends on C3 and C4, but nevertheless, we can see the robustness, because this is enough to guarantee the negative values of this expression here, and C3 and C4 positive. This means I can tune. Of course, the dynamics depends how I tune this one. I am concluding with some results. It's robust, yes. We can see here that also if I have some uncertainties in the mass, as I told you at the beginning of the movie, the mass changes because change the humidity. We can see here at the front of the picture, we can see three lines more or less close each other, but look, if I consider here the sum of square errors for different values of the mass, it is commented here, we don't have, we can see also here much differences, even though we are considering a relative large difference in between. I show you a little bit the results. Here is exactly our internal dynamics. We can see that it seems to be stable, of course moves when in the milling phase. Yeah, we can see here, now is interesting this, between our physical current and our augmented current, or let me say artificial or virtual current inside the microcontroller. This of course depends on the tuning parameter, which is our TI. I didn't emphasize this tuning aspect here, also is something which could be considered in the design. We can see here how we change the hot temperature. Of course, now we can see that we have some degrees during the milling phase. Now, results. I didn't tell you, because it's not the topic of the talk, that very often we bring or we take the system to our desired temperature very slow, because I mean, we can think about a possible profile of the desired temperature, because otherwise the life of the Peltier could be reduced. Anyway, we can see here during the milling phase that the temperature, you can see probably here, changed, but the control try to keep around the desired temperature. We can see that the difference is not so, it's acceptable. We can see how the Kalman filter estimated disturbance, which can be used in the linearization of the input-output linearization of the system, which is in a part of the controller. The controller consists in input-output linearization and these big backstepping elements, which guarantees the robustness. High clamping, new advanced, let me say, this is not our idea, method to fix an object for manufacturing, let me say, idea zero deformation. We don't want to use robots to fix the object, as I concluded also this technical aspect, considering the robustness. The robustness here is guaranteed using this virtual sensor Kalman filter base, with a mix between the deterministic and stochastic method. The stochastic aspects, let me say, guarantees or the help for the robustness, and the controller, thanks to the backstepping, in particular the Lyapunov approach, which is based on an inequality, guarantees nevertheless the robustness of the controller. Okay, thank you for your attention. If you have a question now or after, during the coffee break, we can discuss again.
Yeah, can I ask a question?
Of course.
Yes, it's